Welcome to the Maricopa Project. I'm Nishant Saxena. I am the project manager for the BEST team at Bosch Thermal Technology.
And I'm Tom Kelly for Bosch Thermal Technology. I'm the application engineer.
So today we're going to go through the food factory for Maricopa County's jail system. Here we have 880 collectors. What we're looking at right now is the second roof from the furthest down from the mechanical area. In this roof in specific, we have 2 columns going back and forth, and we have arrays of 7 collectors in each column, and we have a total of 27 arrays.
So this system that we have here, this 880 collectors, it's going to provide a major amount of the energy needed for this food facility, which provides the food for 7 facilities within the Maricopa County jail system. We're going to have a look at where this energy goes down in the mechanical area a little bit later, but it's a tremendous amount of energy. So we're in Phoenix, Arizona. This roof up here probably is about 110 degrees today, and it's not even their hottest day of the year. There's a lot of extra solar thermal energy just bombarding this roof, and this collector system is going to capture a tremendous amount of that energy and make use of it. Solar energy is a tremendous resource that we have all throughout the United States, and we're seeing more and more large-scale projects just like this one in Maricopa going in around the country. One of the biggest advantages of the Bosch system is the fact that our collectors are what we would categorize as low flow. Per collector, our flow rate is 1/4 gallon per minute. So on a system like this, with 880 collectors, you'd expect to have very large pipe diameters, let's say 8-10 inches mains. What we're looking at here is a pipe diameter for the main supply and return of only 4 inches. It's a huge savings when it comes to piping materials, total fill volume, expansion tank sizing, and pump sizing back in the mechanical area.
So from the main supply and the return line, we have it branching out into the collector arrays. And as we've seen here earlier with the 2 columns, we have the main supply and return going under the collector arrays. Here is the return. So we have the supply energy being collected from both of the columns into one pipe and going back out to the main supply.
Each row is broken down into individual, what you can see here, much smaller piping. We're seeing 1/2-inch piping here. What you see coming out of the top of the collector is we have an air vent with a shutoff. Down below we have a relief valve, and then just below that what you see here is an auto flow control. So this auto flow control is going to make sure that the flow rate needed for varying size collector arrays is appropriate for that size collector array. The relief valve you don't see on all systems. What they elected to go with here on this project is to have the ability to isolate every collector row with an isolation valve on each supply return to the collector row itself. In that case, we would always use a relief valve as a safety, just in case that row needed to be shut down and if pressure were to build up. The air vents used during the purging process, it's a critical point of a multi-row application. Its job is during the commissioning so that we can effectively bleed air from the high point of the system.
So what we see here is the black steel superstructure that was put on site by the mechanical contractor, and it was laid out to ensure that the collectors were all even across the roof, because the roof here, as we see, has its curvatures and it's imbalanced. So the steel superstructure was put in place just to balance out the roof on the collectors. And right on the structure we have our Bosch mounting structures. So this here is our flat roof mounting structures, which has a telescopic component and can adjust the angle of the collector from 30 to 60 degrees. In the case with the food factory, we adjusted our collectors to an angle of 35 degrees to ensure that we maximized the output of the system annually.
So certainly in Phoenix, we find ourselves wanting to be in the shade quite often, but we don't want the collectors in the shade. So when you're dealing with a multi-row application, you're trying to make sure that this time of the year the shadow isn't that bad. But when we calculated a row distance between row to the row behind it, we were looking at dealing with the shorter daylight hours of the year in the Decembers and Januaries. So the spacing that you see from row to row has been engineered to make sure that at this latitude we don't cast a shadow from one collector row to the next. What you're seeing here is an expansion joint. Regardless of what you're using as a heat transfer fluid, you have to take into account what's going to occur when we go from temperatures as cool as 60 degrees Fahrenheit all the way up to 220 degrees Fahrenheit. So that kind of temperature differential is going to create enormous and tremendous expansion in the piping. So this type of system, being this large, needs to have the ability to basically flex.
So what we see here is the second form of an expansion joint. This one is steel berated, and the mechanical contractor used it to provide the expansion capabilities for the main supply and the return. So now we're at the mechanical area, which what you see behind us is the 35,000 gallon buffer tank. We have the solar loop pumps on both sides of the heat exchangers. We have the heat exchanger for the solar side, as well as the heat exchanger for the domestic hot water side. We have this gigantic expansion tank behind us, as well as the piping, the fittings, and all the way in the back you can see the collector array coming down.
What you see behind me here is a commercial grade heat exchanger, and there's two of them on this project. The heat transfer fluid that we're circulating through the 880 collectors up on the roof is a deionized water that's been treated. That water doesn't leave the collector loop. The buffer tank water, which is going to be our storage medium, it too, it's a closed loop separated by two heat exchangers which stores the thermal energy that we harvest during the day. That energy is then taken out of the buffer tank through a second heat exchanger and integrated into the domestic hot water system. So what we're looking at here are two of the pumps, two of the circulators that are taking the energy from the buffer tank, bringing it to the second heat exchanger, and then this bronze pump, this domestic pump, is bringing in the domestic water from the domestic storage tank, actually 4 domestic storage tanks inside the building, pulling the heat out and taking the heat out of this buffer tank. Right now what we're seeing on this system, we just fired it up, we're coming out into this heat exchanger at about 70 degrees from the domestic side, and we're coming out of this heat exchanger at approximately 170. So we're picking up 100 degrees worth of energy out of this buffer tank right now. So what we're looking at here to my left is the expansion tank, not a storage tank on this system. You can see that with 880 collectors on a closed loop pressurized solar thermal system, when this system and if this system should either experience an electrical power failure, or if we just do not use the energy that is maxed out in the 35,000 gallon buffer tank, the system's going to shut down. And if the sun is still out, the fluid on the roof will boil, and that's fine. We sized our expansion tank to absorb not only 100% of the liquid expansion, but also the vapor expansion. So this system is completely safe, even during what we call a stagnation period. So hopefully we've given you just a brief overview and a good idea of what an 880 collector system looks like. Here at Bosch, we certainly support you on the engineering side, whether it's pipe sizing, collector field, array sizing, the entire system.
So thank you for joining us in this video. We hope that we provided some information that was useful, and feel free to contact us if you ever need support on a design aspect or with the products.